All right, so we're going to talk about an idea that's fairly similar to impulse. It's definitely related, an idea that's related to momentum called impulse. And impulse is simply defined as the change in momentum. Now, this change in momentum is just a change. So we calculate like any other change or difference, and we can use delta, or we're going to subtract the final momentum minus the initial momentum. So the equation is going to be, well, let me show you in a minute. But first of all, you remember how momentum is P and it doesn't really make any sense? Well, impulse is kind of the same. The symbol for impulse is going to be J. And so here's our equation. J is going to be the change in P, or the change in momentum. And that's really it. So it's kind of a small equation, but there's, as you'll see, kind of a lot packed into that delta notation, of course. Right, and if we were to write it out even further, we would say it's the final momentum minus the initial momentum, and that's going to be equal to the impulse. So impulse is sort of a change in momentum. Impulse can cause, sort of a change in momentum, and it's going to be related to something else. Let's look at this first, though. Let's calculate the impulse when stopping a 15 kilogram object moving at 10 meters per second west. And impulse is a vector. So impulse here is going to be the change in momentum. So again, see if you can figure this out on your own first. See if you can find out what's the final momentum minus the initial momentum. And actually, let me go back real quick, because once you have this, right, you could write this out even further, right? You could say, okay, well, impulse is, I know momentum is mass times velocity, right? So you can say mvf minus mvi. And then you can even go one more step, right, because its m's are the same. And so you get m, impulse is going to be m times v final minus v initial. All right. So this is also a valid way to write it. But back here, okay, calculate the impulse when stopping a 15 kilogram object moving at 10 meters per second west. All right, let's figure this out. The final momentum. Well, if we're stopping it, it should be pretty obvious that the final momentum is going to be 0. Or in other words, it's going to be, the momentum is the mass times the velocity. And the velocity would be 0 because it's coming to rest. Minus, what was it going initially? It was going 10 meters per second west. So again, it's going to be m times v. M here is 15 times v is negative 10. Be careful. That's v, which is a vector. So this is going to be 0 minus 15 times negative 10 is negative 150. So 0 minus negative 150 is just positive 150 kilogram meter per second. Now I said this was a vector, so what is the direction on this vector if it's positive? Well, clearly we're talking east and west, so this would be east. And that should kind of make sense, right? Think about some object moving west. You're going to have to apply an impulse in what direction to make it stop? Well, you're going to have to apply an impulse east. And you may notice in this discussion that impulses seems to be fairly similar to force, right? You would think, okay, well, if something's coming at me, I've got to push it east in order to make it stop. An impulse is actually going to be related to force. And let's look at that relationship, I should say. All right, so you've heard Newton's second law as F equals ma, which is true, kind of. But Isaac Newton didn't write F equals ma exactly. He wrote this, right? He wrote F is dp dt. This is some calculus, and it's never too early to start learning calculus. dp dt means the change in momentum with respect to time. Or in other words, how does the momentum change divided by how does the change in time is a way you can think about it. The only difference is that when we talk about change, this delta, this d, really it comes from delta. The difference is that here, that d represents an instantaneous change, which is what calculus is able to do that regular algebra is not. But again, we said that P is equal to mv, right? So look, you can just rewrite this as dp dt is dmv dt. Now there's something in calculus called the product rule, and in essence you just need to know that the way the product rule works is you take the one of them times the derivative of the other, plus the second times the derivative of the other. So basically, you get this, okay? You have m and v. So one time you're going to take v times dm dt. The other time you're going to take m times dv dt. Now, again, this represents a rate and change, dv dt. How quickly is velocity changing here? Well, what do we call a change in velocity? A change in velocity, that's acceleration, right? So really, this is just acceleration. dv dt is the same as delta v over delta t. It's just, again, this is instantaneous, but again, it's pretty much the same. Okay. This would represent a change in mass with respect to time. Well, how is your mass really changing? For most objects, it's not, right? You and I, our mass isn't going to be changing as we're running or whatever. It's not going to instantly change. So in a lot of cases, this dm dt thing, oh yeah, you see this here, so I'll just write it here, ma plus v dm times dt. This dm dt thing is just going to be 0 for most objects, which means that this whole thing goes away. And you just have ma, so F equals ma. And that's where Newton's second law is. So Newton's second law is, you know what, F equals ma is exactly true for any object whose mass isn't changing, like constantly changing. Can you think of any objects whose mass is constantly changing as they're moving? Maybe you can. A big one would be rockets, right? Because rockets have fuel in them. And the rocket fuel takes up a considerable portion, if not the majority, of the mass of the rocket itself, right? Is just the fuel. So as that rocket burns fuel, this is actually going to be some value, and that's going to make this a lot more complicated, which is, why rocket science is supposed to be so hard. It's not rocket science. Well, this is rocket science if you do dm dt. But again, my big takeaway here, what I want you to see is that Newton's second law actually relates to impulse, right? dp, the change in momentum, over dt is the change in time. Actually, you could just take this thing in the box, right? And as long as we're, the change in momentum is, if we're looking at the change in momentum, that's just j, right? And so you could write this. As long as the mass is the same, you have delta p over delta t, which we can write delta. We know delta p is the impulse. So force is going to be equal to the impulse divided by, and the change in time is just how long did it occur. The impulse divided by time. That's pretty cool. Let's see if that works out. Let's look at the unit analysis real quick. We've been doing impulse, we just talked about impulse, and I didn't tell you because I think that you should understand that impulse, the units of impulse, J has units of, again, it's the same as momentum, it's kilogram meter per second. So let's do some unit analysis. If we have kilogram meter per second, divided by seconds. Oops, that's seconds. I don't know how to divide fractions, so instead I'm going to flip and multiply. Kilogram meter per second times 1 over seconds. And this gives me, multiply across the top, nothing cancels, so I just have kilogram meter per second squared. A kilogram meter per second squared is the exact same thing as a Newton. That's what we call the Newton. So you see that the units even agree with us. It's not just the equations. It's not just because Mr. King says so. It's not just because it was on Wikipedia. It's not just because it was in the textbook. We can see for ourselves. This must be true. If you take an impulse, which is in kilogram meter per second, and you divide it by the time, which is in seconds, you get units of kilogram meter per second squared. In other words, you get units of newtons, which means that must be a force. So we can use this to figure out forces. We can use the change, or rather, I guess I should say, like a force can cause a change in momentum, which is an impulse. So how do you think that relates to car safety? Well, what do airbags do, I guess? What they really do is, look at this right here, this equation. Force is impulse divided by time. Okay, when you're in a car wreck, whatever's going to happen, your impulse is it's set, right? You're going to go from moving to stop. You're moving 40 miles an hour, so your momentum is your mass times 40 miles an hour, and then you're going to stop. That's a big change in impulse. Or sorry, I keep saying that. It's a big change in momentum. That's a large impulse. So the only way to decrease the force here, because you can't make this smaller. There's no way you can make this smaller. What is the only way to decrease the force, to make force smaller in this equation? Well, if we can't do this, what could we do to T? How could we manipulate T to get a smaller F? Well, if we increase T, F will become smaller. So we increase the time. We can't do anything about the impulse, but we can increase the time. And that's exactly what airbags do, you know. If the airbag's not there, your head's going to come in and slam, and it's going to take a fraction of a second to stop. That fraction of a second is going to lead to huge, huge amounts of force. Right? Let's say it takes you 0.1 seconds to stop. Right? So you're going to have some impulse divided by 0.1. That's going to be a lot of force. Right? That's a pretty big force compared to an airbag. Now, airbags don't slow you that much, and it's still going to hurt. I think sometimes people think like airbags are nice, big, fluffy pillows or something, but it's still going to hurt. But you might go from stopping in 0.1 second to stopping in 0.3 seconds. And that's going to make the force 1/3, right? Look, by increasing the stopping time by 0.2 seconds, not very much, you have decreased the force by 1/3, which is a pretty big deal. So that's really what the airbags are doing. They're stopping you're increasing the amount of stopping time to decrease the amount of force from this equation here. All right, let's do one of these. What is the force applied by a baseball bat if it applies an impulse of 40 kilogram per second to a ball for 0.5 seconds? As you'll see, these are usually pretty easy. Sometimes you might have to calculate the impulse, like as a change in momentum, but again, you know, beyond that, it's fairly straightforward. All right, so my force here is going to be my impulse, which is said was 40 kilogram per second, over 0.5 seconds. The force there, 80 newtons. Simple enough. I don't think I'm going to do another. Let's look at what's on the next one. Yeah, I'm not worried about this. Anyways, so that's impulse and how it relates to force. I don't think there's anything else about that, so I will stop the video here. Thanks for watching.